This topic is asymmetric synthesis part 8. So in this I'll be dealing with the enantioselective synthesis, the part 3. This will be the last video of your asymmetric synthesis unit. Okay. So moving on to the enantioselective intramolecular aldol condensation. So here intramolecular aldol condensation means within a molecule the reaction is taking place, like when the two molecules of an aldehyde or the ketone will react in presence of a base that gives as an aldol product, right? So here what happens, you are taking the two ketone molecules within the molecule, okay? So in the presence of that ketone molecules within the intramolecular reaction, within the system the reaction will take place. At that time in the presence of the catalyst chiral base, okay? In the presence of the chiral base you are getting the product with respect to your enantiomeric excess, that much yield of that enantiomeric excess. So for example, if you will see here, so you are taking the S-proline, that is your catalyst chiral base. It will act as a chiral base. In presence that first the starting material will be your cyclopentane 1,3-dione, okay? And cyclopentane 1,3-dione, upon treatment with the S-proline, it ends up with the in this product, okay? It undergoes cyclization with the formation of one adduct intermediate, it leads to the product. So what happens in the first step, the attack of the base, that is the nitrogen which is having lone pair of electron, will go and attack to the carbonyl carbon of your ketone molecule over here, dione, okay? So once it will go and attack, at that time what happens, this bond will shift, make it as a O minus, okay? And after that what happens, there is a formation of this whole adduct, and once it reaches this gives you O minus, right? That will abstract the proton. Once it will abstract the proton, at that time you will get back this structure, okay? So next thing is, you are just showing the complex formation over here, alright? And then in after the formation of this, what happens here is, again this charge shifts back, and then this bond will go and attack over here. There is a cleavage of whole of this moiety, okay? After the cleavage of this whole of the moiety, you are generating with the ring closure reaction, okay? Once there is a ring closure takes place, at that time what happens, the hydrogen atom which is present over here towards this side, this hydrogen will go make one bond, and there is a cleavage of the water molecule. Dehydration will takes place over this step, resulting you in the alkene formation over here. So this is your product which will result in the end up with the enantiomeric excess of 93% of yield, okay? So moving on to next reaction, it is your use of the plus and minus DET in asymmetric epoxidation. This video is very important for your exam point of view, okay? And then moving on to first in this thing, what happens here is when an allyl alcohol upon treatment with the Sharples conditions, okay, upon Sharples condition, there is a generation of the two epoxides. One is your beta epoxide, one is your alpha epoxide. So moving on to here, if it is a beta epoxide, that is your major product because it is having the high yield of enantiomeric excess. So here if you will see, the allylic position will get affected, okay? And if you just go through this point, okay? So enantioselective here substrate must be a primary alcohol, that is over here, and it should affect at the allylic position of that atom. And then allylic position should be attached with the chelating groups such as your OH, NH2, etc. So if particularly if we are taking the allyl alcohol, so OH will be attached over here, okay? So here there are two types of DET, that is your DET is nothing but it is diethyl tartrate, okay? One is the plus DET and minus DET. If you will see here this structure, for plus DET and minus DET, just go through the structures. That will be acting as your chiral reagent, DET, okay? And then moving on to catalytic medium. So this is your catalyst, Alright, so TiOIPr4, that is your catalyst, that is your titanium tetraisopropoxide is your catalyst. The oxidizing agent is your tertiary butyl hydroperoxide. So in all these mediums, like you have to take one starting material and then you have to treat it with the DET. It can be a plus DET or minus DET, and then upon treatment with the catalytic medium and oxidizing agent, and that time only you will result in your epoxide formation. Okay, so here what you are doing is you are taking an allylic alcohols, primary allylic alcohols, and then upon treatment with the minus DET, at that time you will get back the epoxide formation in the front direction. What happens here is, always remember the alkene, whenever it is in the presence of the DET, minus DET, and in the presence of, upon treatment with the tertiary butyl hydroxide, hydroperoxides, and then tertiary butyl hydroxides. Okay, two conditions are there in the presence of again and titanium tetraisopropoxides. So in this condition, what happens, the alkene gets affected. Okay, not these groups, whatever the allylic position that alcohols are present, that and all will not be affected. The main aim is just to affect the alkene, and there is a formation of an epoxide over here. So you will get an epoxide, that is, this is your beta epoxides, and then this is in the front direction, and then this one, it is in the back direction, that is your alpha epoxides. As when upon treatment with the plus DT, you will result in this, and then upon treatment with the minus DT, you will result with the front side epoxides. And then moving on to next slide, it is formation of the DT Sharples reagent. How the reagent is formed? Okay, so you are taking the titanium and tetraisopropoxides, and then if you will treat it with this reagent, that is your DET. Okay, if you will treat it with that, at that time what happens, this oxygen which is having a lone pair of electron will just go and attack to the titanium, and then there is a cleavage of the IPROH. Okay, this whole thing will get cleaved out, this one. Okay, and then again this which is present over here in the same, okay, OH molecule which is present, and lone pair of that oxygen will again go and attach towards this side, right and left, both the sides it will go and attack. So you'll end up with this molecule. Okay, and after that, with the cleavage of the minus 2 isopropyl hydroxide, right, at that time you will result in this moiety, which is also similar to this molecule, to this compound. And so in the back side, if you will write, you can, if you will reverse it, at that time you can write it like this. So moving on to here, if you will take both of these Sharples reagents, okay, at that time what happens, hence the oxygen which is having a lone pair of electron will just go and attack to the titanium, again towards this side, again it will go and attack to the titanium. Okay, first you are showing the linkage, and then after the linkage formation, after the formation of this linkage, at that time what happens, in the crown ethers, you have studied the crown ethers, right? So this will go and attack to the titanium and resulting you in this crown ether structure. Okay, you have to show here, stereochemistry will play a very important role. Remember this always. Okay, so in the mechanism part, what happens here is, you are taking the titanium tetraisopropoxide upon treatment with the allylic alcohol. One of the IPROH will get cleaved out from here. Okay, so you will get back this moiety, and then upon treatment with the tertiary butyl hydroperoxide, right, again one more molecule of your OIPR, because you are treating with the tertiary butyl hydroperoxide. Okay, so this will just go and bind over here, resulting you with the cleavage of the IPROH, with the cleavage of one of the molecule of IPROH, isopropyl hydroxide. At that time you will end up with this attack of the tertiary butyl, and then this oxygen, which is having a lone pair of electron, will just come and attack towards the alkene position, and this again comes and attacks with the cleavage of the tertiary butoxide. Once the tertiary butoxide gets cleaved out, you will end up with this product adduct. And then what happens here is, so when this comes back, at that time this whole thing will go, okay. This titanium, this catalyst will cleave out with the formation of one O minus. Upon treatment with again hydrolysis, as at that time the treatment with the tertiary butyl hydroperoxide, at that time hydrogen will come and bind over here. O minus will abstract the proton from here, resulting you in the epoxide formation. And here why we are showing this one as well is here you are seeing one arrow mark, right? So when we will take the starting material as this, with this condition, upon treatment with the tertiary butyl hydroperoxide also, you will result in this, okay. So because of this we are showing this arrow and we are writing this starting material. Don't get confused with this and this. Just you will end up with this moiety. Here there should be a plus charge, because oxygen which is having a plus charge, first when it comes over here, when this neutralizes, at that time and there is a cleavage of this bond, resulting you in the O minus, that will abstract your H plus, and you will end up with the epoxide formation, which is your major product. Moving on to asymmetric amplification. So in the asymmetric amplification, what do you mean by asymmetric amplification? So what happens here is, in general I will speak about the reaction. So we are taking the two enantiomers, okay. Once we will take the enantiomers, in the presence of the metal complex, will induce the metal in the dissociation state, leading to the formation of enantiomers, okay. That will lead to the formation of your asymmetric amplification. That is called as your asymmetric amplification. So we'll move on to these points. So here what we'll say, asymmetric synthesis is in which whenever we are doing the asymmetric amplification, it is the ultimate method of the asymmetric synthesis, in which the enantiomeric excess of that product will exceed to the chiral auxiliary. So here chiral auxiliary means it will always represent to the stereochemical aspect, okay. So that will only tell you the stereochemical aspects. Stereochemistry will based on this chiral auxiliary used, okay. So recently what happens with benzaldehyde, when the benzaldehyde molecule is treated with the diethyl zinc, in the that diethyl zinc will act as a catalyst, okay. Of that, some sterically constrained chiral amino alcohol, that will give you the 1-phenyl propanol, which is having the higher optical activity. So for example, if we are taking the amino alcohol with the optical purity of 10.7%, but then we are producing the enantiomeric purity of 82%, that will takes place only in presence of your diethyl zinc, that metal, okay. That the reaction will only occur in the asymmetric amplification. That is the speciality of this reaction. So here what happens, it has been explained on the basis of the fact that the bidentate metal, that is your L2Zn, okay. We are taking the two bidentate metal, two types of the complex formation with the chiral ligand, that is, if you will see LR and LS, okay. So if you will speak about the enantiomeric form, it will be LR bidentate metal complexes, LS, and mesoforms can also appear over here, like LS. So this whole forms, enantiomeric forms and the mesoform will be present. And then what it says, the diastereomers of the two types of the metal complex will induce the dissociation state, which will lead to the formation of two enantiomer, and that brings the asymmetric amplification, okay. So moving on to reaction. So what happens in the reaction is, you are taking the benzaldehyde and if you are treating it with the diethyl zinc in the presence of catalyst. Here remember, this is your catalyst for asymmetric amplification. This will be your catalyst, okay, tertiary butyl alcohol with the pyridine attached. So whenever the benzaldehyde and if you will see the diethyl zinc upon catalyst, treatment with the catalyst, you will end up with the product of an alcohol, okay, secondary alcohol. So moving on to reaction, like how it shows, like with the help of an example, if we will show how the alcohol is formed. We are taking the two enantiomers, okay, you can see these structures, like it is similar to the camphene. You can see it as the bicyclic compounds, bicyclohepto compounds. And then if you will take the two enantiomers, that is having the enantiomeric excess of 15%, okay. Upon treatment with the metal catalyst, that is your dimethyl zinc we are taking. So the alkyl group will vary. So dimethyl zinc, upon dimerization, what happens here is, upon dimerization, when the dimerization takes place, there is two dimers which is formed. One is your homodimer, which is less stable, and one is your heterodimer formation, okay. That's all you have to show it about here. In the next, so here what happens, if we will take the homodimer, what happens? So with the enantiomeric excess of 15%, it is possible to the oxymalkylation product with this catalyst, that is your dimethyl zinc, which will lead to the product of more than 95% of your enantiomeric excess. So what happens here is, you are taking the homodimer upon treatment with the ZnMe2, that is your catalyst. What happens here is, first there is a formation of one of the linkage between your starting material and the metal complex, okay, and after that you have to treat it with the benzaldehyde. Once you will treat it with the benzaldehyde, there is a formation of this whole complex moiety. Okay, after the formation of this, what happens here is, this whatever with the starting material you have taken, right, with the metal complex, this whole thing will cleave out. I'll show you here. Here you are forming one bond between the oxygen and the zinc, right? This oxygen and the zinc, which is with the aldehyde oxygen and carbonyl oxygen with that zinc, you are forming one bond. And so what happens here is first this bond will shift, make it as a first it will make it as a negative charge, O minus, with the cleavage of this molecule, okay, and then this gets attached over here. Alright, methyl will come and attached over here. Due to this whole moiety will cleave out and there is a formation of O minus, okay. After the formation of O minus, upon addition with the H plus, the O minus will abstract the proton, resulting you in the alcohol. Thank you. If you have any doubts, please do ask in the comment box.